Take your time. Okay. So hello everyone. Yeah, sorry for starting late. There was a group that was here until 2:35, but we're not going to be too mad at them. Oh, hello. Okay. So yeah, today we're going to do some decidability exercises, which I think are going to be helpful for like maybe two of the four questions in the assignment. I want to first start though with saying that I was finally able to get the tutorial 6 recordings, and they're on learning automata, which is sort of like a bonus topic that wasn't talked about during the lecture. And it's not talked about in the lecture, but it's talked about in the tutorial. And there's a bonus question on the assignment four that honestly, it's actually super easy once you actually look at the recordings. So it's like easy 30 points, I think. So if you find the main content of assignment four difficult, then that's what that question is there for.
I wanted to ask, will we be able to understand this tutorial if we haven't been able to?
Yes. Yes, you will. Yes, you will. I would be doing a poor job if you couldn't. Yeah, so today instead, we're going to be not talking about learning automata. We're going to be talking about decidable languages and recursively enumerable languages. Although I think you've already started talking about like P versus MP stuff, but we'll talk about that next week. Yeah.
So we do bonus points on the assignment.
Yeah.
If you were to get more than 100% on this assignment,
Yeah.
special count for 100 or
I'm not the prof, so I can't really determine that, but I did suggest that as an idea. So maybe if more people will talk to him about it as well, he'll be like, oh, that's actually a really good idea. So yeah, ask him again. But it's also like I would say the assignment four, some of the questions are a bit harder than the previous assignments, so that's why I think it's also nice that it's there. Yeah.
Is next week the last tutorial?
I haven't decided yet. I think we'll see depending on what I cover next week and what the content of the final is. So if there's stuff that I didn't cover in the tutorial, but that's in the final, then I'll do another tutorial to cover. Yeah. 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 No comment for now. Okay. But we can talk about it another time. Okay. Okay. Let's actually get cracking. Let's start by just quickly, I just want to quickly review the definitions of decidable and recursively enumerable languages. So I'm just going to quickly write this, but it's already in your notes. So a recursively enumerable or a Turing recognizable language, that's the other term I prefer, is when, you have a language, which is a subset of sigma star, and there exists a Turing machine M such that L is equal to L of M, okay? So this means that there is a Turing machine that recognizes the language, okay? So what that means is I have some Turing machine M, and when I have a string which is in the language L, right, then the Turing machine is going to say yes, right? It's going to say, yes, I accept this string, right? But the distinction between recursively enumerable or Turing recognizable and decidable is that it doesn't make necessarily a decision when the string is not in the language. So when the string is not in the language, the Turing machine can say one of two things. It can either say no, like I actually reject it. So in this case, it actually makes a decision. Or in another case, right? Or in another case, it can loop, right? So not accepting for Turing machines now means two things, right? So not accepting, well, it can mean one of two things. It can either mean you outright reject it, right? So you actually go to either a reject state or you like halt in a non-accept state, depending on your formalism, or you just keep looping forever, right? So that's Turing recognizable, okay? And it's sort of a weaker condition than decidable or recursive. So a language is recursive or decidable, right? If again, it's a subset of sigma star, but now we have a Turing machine, right? M, which decides, this is the actual like technical term people use, which decides L. So meaning that my Turing machine M when you give it a string W, right? Well, let's make the contrast very clear. When W is an L, the Turing machine is going to say yes. And when the string is an L, the Turing machine is going to say yes. And when the string is not an L, it's going to say no. Okay, so output's no. Okay. So it decides L, right? And of course, L is equal to L of M, right? So it's always going to make a decision, right? For every L, for every string in L, or come on, for every string in sigma star, M makes a decision. It doesn't, keep wondering and keep thinking about it forever. Okay, so that's all great and dandy when you think about it sort of theoretically, but then the real issue becomes when you actually start to manipulate these things and to try to do exercises with them. That's when things get a bit more complicated. So one advice, I'm not going to do it here, but one advice is it's actually quite useful to just study closure properties of decidable and recursively enumerable languages. Okay, it's useful because you sort of start to manipulate Turing machines, and you can sort of convince yourself that they do halt on everything, or they only halt on things that are in the language, and so on. So these are good to sort of um, make sure that you've sort of mastered at least the theory behind, or the ideas behind decidable and recursively enumerable. So I think these were actually covered, like they're at the end of the lecture slides of lecture 15, I believe. Okay. But what we're going to do in terms of an exercise is something I think is a bit more fun. So this is going to be our first exercise. So in this exercise, we're given some non-empty alphabet, and we're also given a family of languages. So a finite family of languages, where each of the languages, right, is recursively enumerable. Okay, and the family of languages partitions sigma star. Okay, so if you don't remember what partitioning means, it just means this is the set of all strings, all possible strings over your alphabet. And then the family of languages L1 to Ln, it partitions F, right? So it does, L1 is this part of sigma star, L2 is this part, L3 is this part. So altogether, L1 union L2 union all the way to Ln, that's equal to sigma star. And then the pairwise sort of intersection between Li and Lj, where I is different from j, is empty. Okay, so that's the partition. And then the question, which was actually featured in a previous assignment of 330, the one that I designed and was very proud of, is to show that for every language Li is actually decidable. Okay, so that's going to be the exercise. I'm going to give you 2 minutes, mostly because I desperately need to blow my nose. So I will quickly rush to the bathroom, but I will start the timer now. So try this out, and I'll be back. Okay. Okay, please watch my. Don't let anyone see my watch. Okay. Question? Question about the question, or question in general? What's the question? Yeah.
So, like, the RD isn't the same as decidable.
Ah, no, no, definitely not. We'll see why in a second. But it's good that you're asking that now and not during the final.
Yeah.
Yeah. Okay. There's 15 seconds left. Just out of principle, I'm gonna let. It's like I would feel bad. We cannot assume specific property. Only that they're RE. Okay. All right. Shut up. Shut up. Okay. Okay. So, normally I like ask what people did, but I think this problem is complicated enough that if I ask someone, then it would sort of, we would get into like a one-on-one chat. So let me just start by showing sort of a solution that probably isn't going to work. So this is my space, right? This is the space of languages I'm dealing with. Let's make this a bit, no, let's make the actual figure bigger. No, that's, yeah, okay. Now, what do I actually know, right? I know that this is sort of the space I'm dealing with, that these languages sort of partition neatly sigma star. Their union gives sigma star, and there's no intersection. The only other thing I know is that each of these languages is RE, right? So L3 is RE, right? That means that when you give it a string, right? When you give, there is a Turing machine, M3, which when you give a string in L3 to M3, then it'll definitely say yes, right? But if you give it a string which is not in L3, right? So from anywhere else, from here or here or here, it might say no, right? It might say, no, that's not in the language, or it might loop. Okay. So what's a definitely wrong solution to doing this, to showing that each of these LIs are decidable, right? Because I want to show, right, my goal, I want to show that for every I, Li is decidable. So to do that, right, to do that, I need to design a Turing machine, or really it's an algorithm is sufficient. It's sufficient for the assignment and the final exam, don't worry. An algorithm which decides, right, which decides Li, right? So for every string you give that algorithm or that Turing machine, it makes a decision, yes, no, that string is an Li or not, and that decision is correct, right? That's what it means for Li to be decidable, right? So what's a potential solution which would be incorrect, right? Well, if I want to design a algorithm for deciding Li, right, this could be one algorithm. So let's call it algorithm A, which on input W, right, on input W, that's just like the Turing machine is accepting, your algorithm is accepting some input W. The algorithm A says, okay, I'm just going to take this string, and because I know that I can do sort of universal Turing machines, right? I can use a Turing machine to run a Turing machine, right? Then I can just say simulate MI on W, right? So take the code of MI and then run it on W, right? So, I have a Python program, I just take it and I give it this input W and I run it, right? Then what I do is I wait, right? I just wait for the simulation to finish. And if MI accepts W, then my actual algorithm A just accepts, right? Just accepts. Otherwise, right? Otherwise, my algorithm A rejects. Right, so you can imagine just in the actual Turing machine that's implementing algorithm A, so in MA, you would simulate M, right? You would simulate M, right? M gets simulated. M gets simulated on running on W. And then when it gets to the accept state, it goes to the accept state of MA. And when it gets rejected, it goes to like all of these reject states. They go to a single reject state for MA, right? That's how you could do it, right? But now there's a huge problem with this algorithm, right? Everyone's nodding their head. Yes, what's the problem?
Since all the languages are recursively enumerable,
Yes.
what have we?
That's right. Yes, very good, right? This is definitely not going to work because, well, yeah, this is not going to work because as Yusuf just said, the language Li, right, is recursively enumerable. So this Turing machine Mi, the only guarantee I have on Mi is that if the string is in Li, it's going to accept, right? But I have no guarantee about what happens when the string is not in Li, right? It might loop forever. And so in that case, I'll just be waiting at this if statement forever, right? So this is not good because Li is Re, which means that Mi, no guarantee of halting if W is not in Li, and so then might wait forever at this if statement. Okay. So that's kind of a problem, right? We can't do that. Yeah. Do you want to tell me what to do or?
Quick question.
Okay.
F is finite.
Yes, F is finite. Yeah, that's very important, right? If F was not finite, then it's actually still doable. That's kind of interesting, but it's a bit harder. Yeah. It is doable, but it's a bit harder. So so that's not going to work. But what is going to work is using this observation that if I look at my partition of sigma star, right, I have a finite number of languages, right? And I know that these languages, they partition sigma star. So what does that concretely mean? That means that if I have any string in sigma star, right, this string is going to end up in one and exactly one of the languages, right? And when it is in one and exactly one of that languages, that means that this Turing machine, right, this Turing machine like Mi, is going to eventually accept it, right? So what that kind of tells you is then I should simulate running the string W on all of my Turing machines, right? Because what will happen, right, is if I have, Turing machine M1, M2, M3, all the way to Mn, and I give each of these Turing machines the input string W, right? And I make them run. So maybe M1 loops forever, right? Maybe M2 rejects, maybe M3 loops forever. But at some point, right, there has to be one Turing machine and exactly one Turing machine. Maybe let's call it MJ, right? Which eventually accepts, right? And so if this is the algorithm B for deciding Li, all I need to do is I need to run all these guys in parallel. And I wait for one of them to accept. I know that's going to happen. And then when one of those accepts, I just check whether this J matches the I, right? So if J is equal to I, then that means that I do accept the string W because it's actually in Li, right? Then I accept W. Otherwise, right, if MJ accepted W, right? MJ accepted W, but it wasn't the Turing machine for Li, then that means that string W was not actually in the language Li. It was in the language Lj, right? So then I reject W. Okay. So that's going to be that's the idea actually. So just to be on the safe side, I'm going to actually write out the algorithm just quickly. So there are actually two ways of writing out this algorithm. The way I'm going to use sort of leverages the fact that I have a sort of finite number of Turing machines. If you didn't have a finite number of Turing machines, you would have to do something called dovetailing, which sadly I don't think was covered, and I don't have the time to cover it here. But it's actually a really cool technique, so I might link it because it's really cool. But yeah, and I can talk to you about it after if you're interested. Yeah. Okay. So what does algorithm B, which actually works, look like? So algorithm B. So algorithm B is supposed to decide the language Li, right? So let's say on input W. So this is supposed to decides Li. So on input W, what is it going to do? Concretely, right? Because you don't actually, at least in practice here, if we're dealing with a single tape Turing machine, you can't actually run things in parallel. So what you actually need to do is you need to run each of the machines for a certain number of steps many times. So you're, oh, okay, you're not confused, but I think that might be confusing at first. So let's just see how that's actually done. So M is going to be the number of steps I run each of the Turing machines for. So M is in the set of natural numbers, right? So this set is technically infinite, but at some point I'm going to terminate. So this is the number of steps. And then I go through each of my Turing machines for J in 1 to N, right? Right, so I choose the number of steps I want to run each of the Turing machines for, and then I do this for each of the Turing machines. So I run, what I'm going to do is I'm going to run MJ on W for M steps, right? And this M steps is actually very important, right? I don't just say run MJ on W, because if I did that, MJ might loop, right? And so I might get stuck here, right? That was the major problem with this guy is I just said simulate, but I didn't say for how long, right? In this case, I say for how long, right? So I simulate MJ on W for M steps. And what I check is if, right. So if MJ is still running on W, right? So if MJ is still running on W, that means it hasn't made a decision yet. So I just sort of continue to the next Turing machine. So I'll just continue. So I'm going to use like a Python continue statement, but you could also just say, I don't know, continue to J plus 1. Okay. Otherwise, right, if MJ has stopped running by the step M, right, by number of steps M, then I don't immediately accept, right? Because maybe it stopped running by step M and it rejected the string, right? So if, right, so then what I can check is if MJ accepts the string W, right? If it rejected that, I don't actually care, so I'm not going to check for that. But if it if MJ accepts W, then I do this sort of check here, right? Then I check if J is equal to I, I accept. Otherwise, I reject. Okay. So now if we look at this, I think the better way to understand this algorithm is after I've written it down, right? So if we look at this algorithm and we consider this picture again, let's copy it and put it here, right? So I know that eventually one of these languages, right? Well, I know that one of these languages contains the string W and only one of those languages, right? So concretely what that means is that there's a certain number of steps after which the Turing machine for the language that contains that string is going to halt and accept it, right? So I'm going to do this slowly though, because I don't know how many steps it takes and I don't know which Turing machine it is. So I'm just going to simulate each Turing machine 1 to N for number of steps 1 to whatever. And at some point, one of them is going to halt and accept. And then I just have to check if the one that halted and accept was the one for I. If it is, then I accept because that means that it was an LI. Otherwise, it wasn't an LI. Okay. And this was a fairly specific, I guess, example, although I think it was good to sort of illustrate this general point, which was, I would say, the takeaway. So the takeaway of this exercise is that we can sort of create algorithms which use Turing machines as subroutines, right? But we need to be careful about them looping. So like concretely, something like run M on W, and if M halts, do X, otherwise do Y. This is almost never right, okay? Because typically you have the scenario that M might loop, and so you might never actually get to this otherwise. So that's something to keep in mind for assignment 4 and the final exam. Okay. Any questions about this? Yes, Angela. Yeah. Yeah, that's it. So your question is, why is this, there's no bound, right? Yeah, exactly, right? But you know that eventually it's going to get accepted by some number of steps, right? You just don't know how many steps, so you just keep incrementing. I guess you assume that it's an unbounded set. Yeah. But then it gets a bit pedantic, but anyways. Yeah. Okay. So we're good? Yeah? Okay. Excellent. Okay. So that's great. The next thing I kind of wanted to talk about, so this was sort of my attempt of review of like decidable Turing recognizable languages and their connection with Turing machines. The next thing I kind of want to do is I want to talk about the what I would call the undecidability hierarchy. And the way to go from sort of one level of the hierarchy to another, which is a technique known as reductions. So what we're going to do is we're going to sort of review some of the stuff you saw in lectures 16, 17. And I'm going to give a few additional details about reductions. So I believe you've already started reductions, but for NP completeness. So have you? Yes, sort of. Okay.
Because we have like fire.
You had fire alarm. Oh, lucky. Oh. So why is there not that many people in the tutorial? I guess they saw the fire alarm and they just left. They're like, even the tutorial is on fire. Okay. Okay, then you might not have seen reductions yet, but you will very shortly because they're used to show that something is NP hard. They're also used to show that things are undecidable, although you didn't talk about that all that much. So as a sort of primer to reductions, that's what I'm going to be discussing as well. Okay, but enough talking. Let me just actually draw something. So when I talk about the undecidability hierarchy, I really just mean this Venn diagram, which you've seen several times already. So you have the set of languages which are decidable. For instance, AN, BN, CN, AP, where P is prime, and so on, right? And then you have a much larger set, actually, infinitely more large, of problems which are not decidable, but they're recursively enumerable. So these are undecidable, but recursively enumerable. So a fun fact, which is not that fun, these are actually, recursively enumerable is not actually used anymore in theoretical CS. The more modern term is computably enumerable. Recursive sort of is due to like recursive functions, which were sort of from the 1920s. So we sort of stopped using that term. But anyways, it's not that interesting. And then outside of the set of recursively enumerable functions, you have the set of sort of non-recursively enumerable functions. So we know many examples of decidable languages, but now what are examples of languages here and here? So you saw two in the lecture, right? One that was undecidable, but recursively enumerable was here. It was called something like L sub U, right? Which was like, I don't know, a very poor name. It was something like Universal Turing Machine. Okay. That I don't, anyways, I have a bit of a beef with that kind of naming, but it doesn't matter. And then you also saw a language which is not even recursively enumerable. That was the language L sub D. So that was sort of shown to be non-recursively enumerable with a sort of diagonalization argument. Okay. So what I want to mention quickly is that talking about languages sometimes is a bit confusing, and the easier way to understand languages is through their sort of corresponding decision problems. So it turns out that there's sort of a easier way. So an easier way of understanding L sub U is as a decision problem. So DP for short for decision problem. Okay. So a decision problem is just a problem where the answer is yes or no, right? So you have to make a decision. You have to say either yes or no. So the actual corresponding decision problem for L sub u is something like the acceptance problem. This is the name that's typically given to it. So the acceptance problem is something like given a Turing machine M, and some input string W, does M accept W? Okay, this is the acceptance problem. Okay, but the acceptance problem is basically the same exact thing as L sub u, right? So the reason why is because AP is the same as LU because sort of decision problems and languages are sort of in a one-to-one correspondence. So the reason for that is because I can take all of the instances of the, in this case, acceptance problem, where the answer is yes, and then encode them as strings and put them in a language, right? So that would be the language sort of corresponding to the AP problem, which is, so this is the same as the L sub u problem. So this is all of the strings. So all of the instances of the acceptance problem, where when you encode them as binary strings, so this is what that means. So this is just a binary encoding of MW, right? You put them in the language. So where M is a TM, W is a string, and M accepts W. Okay, so there's like this one-to-one correspondence, which is often helpful to think about when you're dealing with languages, because I think as computer scientists, it's easier to think of problems, but then we've been studying languages until now, so that's why we're continuing to deal with that sort of terminology. So this is maybe just a clarification note, is a bit less tutorially and more lecture-y. So what's my actual point here? So we showed, well, you showed, or Jérôme showed in the lecture that LAP was RE, but not decidable. So what does this actually mean? Like, we know what it means in terms of a string, but it's a bit easier to think of as a problem, right? So as a problem, if the corresponding language is not decidable, that means that the original acceptance problem has no decision procedure. Like, there's no decision procedure that you write some code, and that code works when you give it a string, you give it a Turing machine M and a string W, and it decides in finite number of steps whether M accepts W. Like, there's no procedure to decide that problem, right? So that's what it means for the sort of corresponding language to not be decidable. And then what does RE mean, right? So RE means, in terms of the actual problem, if the answer to the decision problem is yes, right, then you can check that the answer is truly yes, right? But if it's no, you have no way of checking, right? That's what RE means in terms of decision problems. So I think it's easier to think about it that way. Okay. So it's not decidable. Oh, okay. It's not decidable. And so how did we actually show? So it was shown to you that AP or L sub u was not decidable using the reduction LD to LU, something like this. Okay. So I don't think, at least I looked through the slides quickly, you didn't really explicitly talk about this notation yet. And I think it's important, maybe he'll talk about it in the lectures, but I think it's important to go over again. So this essentially, this symbol, when you're dealing with languages or problems, this is what is referred to as sort of a reduction. So the more specific term, in this case, it's a mapping reduction, but you don't have to worry about the actual real name. So what is actually a reduction? What were you actually doing in the lecture? So you were doing something like, well, let me just write. So when you write something like P less than or equal to Q, or the language L sub P less than or equal to L sub Q, this sort of process, right, the reduction of P to Q, that's typically what you say, is a method, right? So it's a method to show that Q is, I like to use this term, at least as difficult. Difficult as P. Okay. So I think that's intuitive from the less than or equal, right? So if Q is greater than or equal to P, it means that Q is at least as hard as P. Okay. So how do we usually do this, right? How is this done? And this is exactly what you're going to do in the lectures for NP hard reductions. You're essentially going to show that if you could solve Q, right, you could also solve P. Okay, this is the general strategy. Okay, if this is confusing, just think of like two exams, right? I have exam 1 and exam 2, and I go ask my friend who's done both exams, right? What did you think of the two exams? And my friend is like, if you can solve exam 2, then there's no problem. Exam 1 is super easy, right? So that's the method that you use to show that there's sort of a reduction from 1 to 2, right? This is the general process. You say, well, if you know how to solve exam 2, you have the techniques needed for 2, then you can solve exam 1. That's essentially what you do, but in the sort of decision problem space. Okay, and why do we do this? Why do we do this? I can give you a concrete example with this thing that you sort of saw in lecture 16, I think. So if you show this kind of reduction, right? It's sort of I would say like a 3-step process. So you establish the reduction, right? So you establish the reduction. So LD, or let's say LU is at least as hard as LD, right? So you establish this, and then you say, well, I already know that LD is undecidable, right? So LD is impossible, right? Just like in terms of intuition, LD is impossible to solve. LU is harder than LD, right? So what that tells you is LU is also impossible, right? Just because if LU was possible, then I could use the technique I used to solve LU to solve LD, right? So then 3 is, I conclude LU is impossible. Okay. Bless you. Okay, so this was a lot of review. Now, what I want to do is actually give an example of this, but it's going to be an example in the sort of decision problem undecidability space. So in this example or exercise, we want to show that the halting problem is undecidable. Now, unless you're already familiar with 330, you might be asking yourself, what is the halting problem? It's exactly what it sounds like. Given a Turing machine M and some string W, does M halt on W? Okay. So I'll give you like a minute or two to think about it, but the hint is that you need to do a reduction from, well, you can do many reductions, but the one I recommend is something like AP to HP. Okay, so try this out. Actually, Can you actually try this out? Have you seen reductions? Plus ou moins? Okay, so I'll give you maybe 1 minute. I guess you haven't seen reductions. Okay. Yeah. It can be, yeah. You could do PCP to halting problem, but that would probably be very difficult. Okay, you're not familiar enough to even know what to do, basically. Okay. Okay. Okay, then let's say I give you 50 seconds. Oh, 49. Oh, damn. Okay, and let me actually show you what the general strategy is. Okay, because if you don't know the general strategy, this problem is impossible, which I guess is ironic. Okay, so how do I do acceptance problem reduces to halting problem? Okay, so essentially what I want to show, right? Now there's in the slides, the reductions are sort of shown just as like text. I think it's much easier to understand a reduction by sort of using a few diagrams. This is what Prakash used to do, and I think his method was very good. So that's what we will do. So how do I do this reduction, right? Remember, the intuition is to show this reduction, I have to show that if I can solve HP, I can also solve AP. So what does that tell me? That tells me that in the reduction process, I should be able to design an AP solver, right? I need to create some machine, something that, given a Turing machine M and an input string W, it gives me yes when M accepts W, right? And it gives me no when M does not accept W, right? So I have imagine I have the code of M, right? I have like a Python code of M. I have the input I'm going to give to Python, right? And then the AP solver is supposed to say, just on inspecting this code, I can tell you, yes, it's going to accept, or no, it's not going to accept, right? And to create this AP solver, what I need to use in this reduction is the HP solver. So I have my HP solver. Okay. So what's like one thing that, if you didn't know if you didn't know how to start a reduction, you might try first. This is always a good idea to sort of, it's always good to test this idea to see what's going wrong and how you can fix it. You could just say, well, why don't I just take this pair, M and W, and just give it to the HP solver, right? So let's just see what happens if I give it to the HP solver. So I give M and W to the HP solver, right? Now, what's going to happen if I do this reduction? Well, if M accepts W, then the HP solver, right? What is the HP solver going to say? It would say yes, right? Because M accepting W means that M at some point halts on W, right? So then the HP solver would say yes. Okay. Now, if M does not accept W, then what does the HP solver say? We don't know. Very good. Yes. Then the HP solver says, I don't know, right? Why? Because if M does not accept W, it either means two things, right? It either rejected W, right? In which case it halted, and then HP solver would say yes. Or in the other case, right, does not accepting also means that, could also mean that M loops on W, in which case the halting problem solver would say no, right? So we don't know, right? It could either say yes or no. So that means we wouldn't actually have an acceptance problem solver. We would have a solver that's no good, right? So the point of the reduction now is to actually somehow modify this kind of state of things, so that when M accepts W, my this entire AP solver says yes, right? And when it does not accept W, it's not that I don't know, it's that it does always say no, right? So what I need to do actually then, if I copy this, what I need to do actually is I need to somehow modify M, right? So what I'm actually going to do is, I mean, W is going to stay the same. It's going to be the input to the HP. But M is going to get modified to M prime. And so to do that, I need to take M and I need to give it to something, some computable function actually, that modifies M in sort of a computable way, right? So I need a modifier of M, okay? And this is exactly the same thing as when you do sort of something like NP hard reductions. When you do NP hard reductions, you take an instance of the clique problem, and then you try to convert it to an instance of 3SAT, right? And then you say, well, if I had a 3SAT solver, then I should get yes when the answer to the clique problem was yes, and no when the answer to the clique problem was no, but only using the SAT solver and the modification of the instance of the problem, right? Okay, so now how do I modify? Maybe that's the question. How do I modify M in this case? So how do I modify? So the question really just becomes, so the problem just becomes, how do I modify M to M prime such that, right, such that when M prime and W given to HP, that leads to a yes, then this means that M to W given to sort of HP is yes. And when M prime and W is given to, well, the solver, right? When this instance, this modified instance, the answer is no, then the original instance, its answer should also be no. Right? Like I want this because I want to sort of preserve, like if the answer was yes, but I didn't know that it was yes, right? I should obviously expect that my solver would allow me to determine that it was yes, right? So a yes should be transferred to a yes, and a no should get transferred to a no, right? That's not what we have here, right? A yes gets transferred to a yes, but a no gets transferred to I don't know, right? Either yes or no. So that's why it's not a good solver, right? So now this is the modification this is sort of the crux of the problem is just to create the modification. Okay. So now what is the modification going to be? So I'm going to take my Turing machine M, right? So M is a Turing machine, right? M is a Turing machine. It's got an accept state. It has intermediate states with transitions, yada, yada. Okay. And let's just, for the sake of simplicity, assume that there's only one accept state, right? That's not a very hard assumption to make. If it had more than one, just make them all go to a single one, okay? So it has a single accept state. Okay. Then how do I want to modify this machine? Well, if M accepts W, right? If M accepts W, at some point, it's going to get to QA, right? So then what M prime can do is, as soon as you get to QA in M, right? Go to an accept state, right? Go to an accept state in M prime, right? So I'm going to make this no longer an accept state, and I'm going to make the accept state outside in M prime, right? Now, what else can happen, right? The other two things that can happen is M rejects W, right? So what happens if M rejects W? M, does computation, it goes through the computation, yada, yada. And at some point, right, it stops not in QA, right? It stops not in QA. Okay. But what I want that to be for my HP solver is a no, right? So what does that mean if my HP solver says no? That means that I should loop, right? Okay, so how can I, when my machine M rejects, loop?
Just make.
Yes, right? Well, yeah, you could do that, or you could just say, well, when you sort of stop, right, you just go to another state that just loops forever, right? So I just make new transitions. I make new transitions, right? This is a new state in M prime. Let's just call it Q loop, where you just have a self loop on, I don't know, like all of the symbols, right? And then, if M loops originally on W, then I don't have to do anything. It's just going to keep staying in here, right? So now I think even if you're watching the recording, hopefully you are. Is this recording? Okay. If you're watching the recording or if you're in the room and you're not Yusuf, you're probably extremely confused. Or maybe not, I don't know. So I would say whenever you deal with reductions, you just try something. Like I know that this is going to work, but I can totally understand why you're like, well, what the hell is this? So the way you really want to do reductions is you just try something and then you analyze it. You see if it works. And if it doesn't work, you go back and you sort of modify the reduction, right? So that's why I sort of did here. I started with something that didn't work. And then I sort of told myself, well, it's because on rejection, I don't know, on rejection, that is a yes, but it should be a no, right? So what I need to do now is I just have to sort of analyze this new machine to sort of convince me that it works, right? So why does this work? Right? Well, okay. If, right. So if when you take M prime and W, right? So what I did here was I started with M and W. I gave this to the modifier. It did this thing, right? It modified M in such a way that I got M prime. And then I took this M prime and this W and I gave it to the HP solver, right? So if my HP solver, if M prime of W given to the HP solver returns yes, what does that mean, right? If the HP solver returns yes, it must be because M on W at some point went to QA and then M prime jumped to this QA prime, right? There's no other way for M prime to have halted, right? Because if M on W rejected, it would be looping here. And if M on W looped, then it would still be looping here, right? So the only way for M prime to have halted on W is for M to have accepted on W, right? So returns y. It must be because M on W ended in QA, right? So if it ended anywhere else, and halted, it would loop at Q loop. Okay. Now, what if the HP solver said no? If the HP solver said no, right? Then what I need to guarantee is that M did not accept W, right? Well, if the HP solver said no, that means that M prime on W looped, right? So if M prime on W looped, what does that mean about M on W? It either means that M looped on W, right? In which case it did not accept it, or M rejected W, so it did not accept W, and then it looped in M prime, right? So in either cases, right? This means that either M rejected W or it looped on W, right? And in both those cases, right, that means that M does not accept W, right? And so this no, right, this no that the HP solver returns here is actually correct. It's a no, it's correctly no, because the original MW does not, the original M does not accept W. And the original M only accepts W when the HP solver returns yes. Okay? And so then, so that means, right? So let's just write, so therefore, AP reduces to HP. Since AP is undecidable, so is HP, because otherwise, if HP was decidable, then we could use this technique, right? We could use this technique to decide AP. Okay, so I think you had a question, and then we can get to Yusuf. Yeah.
Yes. Scroll up.
This thing?
Down. The transition in the modifier.
Oh.
Yeah.
Oh, here.
Between QA to the actual substate, is that like an epsilon transition?
It's just no, that's a good question. So it's something like for every X in the tape, X right.
And it works with blank.
Yeah. And then here, right here, to go from here to here. So remember, we can't use non-determinism, right? So we use all of the transitions that don't output from here already. Because if there are transitions that output from there already, then you would keep the machine would keep working, right? So otherwise you go here and then you loop. Yeah.
When you explained that, like, if it's a yes,
Yeah.
it's a yes.
Yeah.
If it's a no,
Yeah.
the same thing as like we could just do like the same proof by saying if n gives a yes, then n prime gives a yes, and if n prime gives a
Yeah.
yes.
Yeah, absolutely. Yeah, for sure. Yeah, it's what I did was let me think. What you're doing is the contrapositive, and what I'm doing is if and only if. Yeah. So they're both the same. Yeah. You could definitely do what you just said. Yes, absolutely. Yeah. Another question or no?
Yeah, when we do the reduction.
Yeah.
So basically, we're just like all we have to do to do reduction, we just have to map the input of the problem we're trying to reduce from the input to an input of the problem we're trying to reduce to.
Yeah, that's right.
Then do like.
Yeah. So basically, yes, very good. So reductions are essentially two steps, right? The first step is to do the instance modification. And then the second step is to show correctness. Yeah, that's it.
So if I give an algorithm that like transforms input into input, that I prove that it's correct.
Yeah, you're done. Yeah. So like if it was something like I don't know, like click to 3-sat, right? Then to do a reduction like this, you take like an arbitrary instance of clique, and you have like a polynomial time algorithm that converts it to a particular instance of 3-sat. Then you show that algorithm like exists is in polynomial time. That's the first part. And then you show correctness that, if the answer to clique was yes, then 3-sat would say yes. And if it was no, then it would say no, or what you also said.
For the idea for here, we still have to do polynomial.
No. So yeah, so this is for, so there's actually a distinction. In this case, when you do, so this is for like an NP, for those who don't really know yet, this is like an NP hard reduction. So the actual technical term is like, this is a Cook reduction or a polynomial time reduction. And usually you actually denote it this way.
Oh, yeah.
Because you want, so for this one, this is a mapping reduction. So it's usually used with a subscript M. And the only thing you need to require is that in a mapping reduction, the modification has to be computable. So it actually has to be possible to do it in finite time. Yeah. Yeah.
I actually also have the question.
Okay. That's as many as you want. Yeah.
The reduction thing, how do you know which language or like which algorithm is harder than the person?
Oh, that's okay. So the question is, how do you know which problem is harder than the other?
Yeah, I probably.
Oh, that's a research question,
Oh,
which is not unsolved. But for the purposes of 330, at the end of the semester, you'll have seen a bunch of problems, and it'll be fairly clear. You'll just have to think about it a little bit. It'll be fairly clear which problem is easier to show that is harder than another problem.
you would accepting problem, you're solving it, and we just change the acceptance. You do like and then applying, then applying.
Solver, yeah. Yeah.
The second question would be, which states do they go to the looping?
Which states go?
Yeah, the representation, we,
Yeah.
like, yeah, we do the arrows from each, I don't know if it's from each state, I wanted to.
Yeah.
know how people which states the arrows from, so that we can,
So it's all non-accept states of M go to Q loop. So why? Because if it's a non-accept state, then like rejection for Turing machines means that you halt at a state which is not accept, right? So that's rejection. So what I want to do is I want to take rejection and convert it to looping, right? So I do that by saying, well, when I finish at one of these states, go to the looping state. And then I just keep looping.
it's like, what if it has, it goes to an exact state, yeah.
Well, you don't care that it has an arrow here, right? Because if it has an arrow here, maybe it's, let's see, how do I answer this? Like, you don't care about the outgoing transitions for a given state. You just care whether it's an accept or non-accept state. Because you care about what happens when the Turing machine ends in that state. You don't care about where it will go next. You just care about what happens when it finishes there. So when the Turing machine finishes at QA, it accepts. When it finishes anywhere else, it rejects. But I want to convert a rejection to a looping. So I say, let me add a transition here where when the machine finishes at this state, I'll go to the looping state.
Okay, so but if it stays and like if M is undecidable, then it might loop inside of M, whatever not all loop. So
If M is undecidable,
yeah,
so machine can't be undecidable. It's a language.
yeah, the language is undecidable.
If the language is undecidable,
So the machine loops in itself, it doesn't halt.
right, so that's fine, right? If M is given an input where it loops, then M loops, right? But M prime is simulating M on W. So M prime is also looping because, imagine you have a Python function which just loops. It's like a while true, right? And then I have a larger Python function that just calls while true, the sort of subroutine. Then the larger Python function also loops, right? So M prime, which is the larger function, also loops. Good? Good, Rita? Yeah. Okay. Angela, good? Ashika, good? Yeah. Good. I don't know your name. Hugh? Hugh, good? Okay. Jonathan, you're good? Wow, there's enough people for me to enumerate all of them.
By the way, when actually receive this, I have to put values, not to write out the algorithm, or just, that I can say that it's an arrow go to the.
Yes. Yeah. So I should just mention, on the slides, it's like written in text. So I just think it's easier to visualize this way, but I will like post the written version, which I think is what you're talking about. It's very easy to convert it to the written version. Okay. Okay. So I have one last thing left, which is also relevant to the assignment. And it's about Rice's theorem. which you've seen. Sorry, did you start packing already? Okay. So that was seen in lecture 17. And the main motivation of Rice's theorem, is that reductions are hard. Okay. Sad face. Okay. So is there some kind of like trick we can sort of employ to make our life a bit easier? Yes. There are times where we can use Rice's theorem to just immediately show that something is undecidable. Use Rice's theorem sometimes, right? Sometimes, not always. You can sometimes use, hello. Oh, I guess it doesn't want to know about Rice's theorem. You can sometimes use Rice's theorem to show a decision problem is undecidable. Okay, so when are those sometimes? So they're specifically when it's about asking something about a property of a language. So it's when you're asking a question about a property of a language. So properties of languages, which are just formally like families of languages. So one property could be, so an example of a property could be L is context free, right? So if you take sigma star, right? Or actually, if you take the power set of sigma star, so the set of all possible languages over sigma star, then L is context free is sort of like a binary partition, right? So you partition the set of all languages over sigma star into is context free and is not context free. Okay, that's an example of a property. Another example of a property is the length of the language is greater or equal to 330. Why 330? I'll let you figure it out. Another example would be something like, is this string 010 in L? Right, that's another example of a property. So you can imagine like this property partitions the power set of sigma star like this. Maybe this property partitions it this way. Maybe this property partitions it this way, right? But it's always like a binary partition on L does satisfy this property or L doesn't. Okay, so what does Rice's theorem tell us about this? So Rice's theorem says the following thing. Whenever you have a decision problem about a non-trivial property, we'll get to what that means in a second. Trivial, I guess you've already seen it, but I'll just review it. Whenever you have a decision problem about a non-trivial property, that decision problem is undecidable. Okay, so the only sort of new thing here, new in the tutorial, but hopefully not in the lecture, is non-trivial. So non-trivial just means not always true or not always false. Okay. Okay. So if you have, for instance, the decision problem, given a language L, is L context free, undecidable Rice's theorem. If you have another problem, decision problem, given a language L, does the language contain more than 330 strings, undecidable Rice's theorem, right? So that's pretty nice. You don't have to make the reduction for it. So let's look at a bit more concretely some examples. So are the following decision problems decidable? Okay, let's look at decision problem 1. Given L, which is subset of sigma star, is L greater or equal, the length of L greater or equal to 0, right? So is this decidable, undecidable? We don't know. Let me give you like 20 seconds. No, 11 seconds. Is it decidable, undecidable? Decidable, undecidable. Undecidable. Oh. So I give you a language. It's a subset of sigma star. Uh, greater than or equal to 0.
Oh.
Aha. Right. So the question is, I give you a language L, it's a set of strings, and I ask you, is the size of L greater than or equal to 0? Well, it's trivially true. Yes, right? This property is trivially true. Aha, I tricked you. Even Yusuf. Wow. No. I agree. If it was strictly greater than 0, then undecided. Yeah. But this is trivially true. Any L subset of sigma star has cardinality greater or equal to 0. Yes. Number of elements. Yeah. So of course it has greater or equal to 0 elements. It can't have -2 elements. That would be like L owes you strings, which would be ridiculous. Okay. Another decision problem. Given L subset of sigma star, is L Turing recognizable? Okay. Let's take another 10 seconds. Okay, 10 seconds have passed. Not decidable. Yes, very good. It's undecidable, right? Why? Well, the first thing is this property of a L being Turing recognizable. So this property is not trivial, right? I have one example of a language which is Turing recognizable, right? So a yes instance would be, I don't know, AN, BN, CN. That's even too much, right? Like AN, that's Turing recognizable. And then a no instance, I have it from the lecture. No instance is just the L sub D language, right? So it's non-trivial. And so by Rice's theorem, right? So by Rice's theorem, yeah, not decidable. Some would say undecidable. I'm not one of those. Okay. Okay. Last one. DP3. Okay. Given a Turing machine, M, does M accept W, well, I guess W in sigma star within n steps. Right? So this decision problem, it's you get 3 inputs. You get M, W, and N, and you're asked in n steps, does M accept W? So let me give you 10 more seconds. Oh, you have a question? Okay, let me give you more time and I'll just answer the question. Yeah.
For the like non-decidable, is it for the decision problem, the language itself?
The decision problem and the language itself. So it's like a one-to-one. If you say a decision problem is undecidable, its corresponding language is also undecidable. Yeah. Okay, let's just wait. Let's just wait 15 more seconds. I'm gonna finish on time for once. That's kind of crazy. What? Right? And we started late. That means I should have had more content. I mean, I do, but anyways. Okay. All right. So what do we think? Undecidable. Okay. Well, let's see. Why do you think it's undecidable?
So I think I can come up with a Turing machine and it accepts. I think I can come up with a Turing machine and it accepts W within n steps.
Okay.
I'm not sure.
Okay. Yeah.
I think it's decidable.
Oh, why do you think this?
Well, first of all, intuitively,
Yeah.
I think you could check it.
Oh,
And also, I, I think it doesn't partition. I
aha,
think you can have some things on both sides.
aha, aha. Okay, so there are, yes, very good. So there are two things here. The first thing is that actually, in this case, Rice's theorem does not apply. So Rice's theorem does not apply. So you can't always use Rice's theorem. Please remember this. And please remember that I told you to remember this. Okay, Rice's theorem does not always apply. Okay, this is not a property of a language. It's a property of a Turing machine, right? Not the same thing. And the second thing is I can come up with actually, we kind of came up with a decision procedure together of this problem, right? What's a decision procedure? Run M on W for N steps. And so you wait for N steps, and then you check at the end, has M accepted W? If yes, you accept. If no, so either it's still running or it's rejected, either at that point or earlier, right? Then you reject, right? So then it's actually decidable. Just run M on W for N steps, like we saw at the beginning, and check if it accepted. If yes, accept, else reject. And there you go. There's a decision procedure. All right. And that's all I wanted to cover. Are there any final questions? No questions? All right. Well, thank you very much for coming. And yeah, next week we'll do some PCP stuff. We'll also do something like related to question 1 of assignment 4, because we haven't really done something that can help you for question 1 of assignment 4. Like there you have to kind of, let me stop recording. There you